Today, IMS serves as a growing hub connecting researchers, engineers, industry professionals, and government institutions. At IMS, we connect, develop, and innovate. We bridge research, innovation, and real-world applications by fostering collaboration across academia, industry, and government. We believe that progress begins with shared ideas and strong partnerships, and we are also committed to empowering the next generation through education, training, and mentorship, supporting young scientists and engineers to become future leaders. At the global level, IMS actively builds international collaborations, creating opportunities for Indonesian talent to contribute to cutting-edge research and the global magnetic community. Our work is driven by 4 key pillars: scientific meetings, research dissemination, education, and support for energy magnetics development, powering technologies such as electric vehicles, generators, and sustainable energy systems. IMS is more than an organization. It is a platform for connection, a center for development, and a force for innovation. Indonesian Magnetic Society, advancing magnetism for Indonesia and for the world. Let's join us.
Cek. Assalamualaikum warahmatullahi wabarakatuh. Good morning and a very warm welcome to all distinguished keynote speakers, invited speakers, presenters, and all participants. We are delighted to gather here once again at the Graha Cakrawala Universitas Negeri Malang for the second and final day of the 4th International Conference on Magnetism and its Application 2026, ICMIA 2026. I'm Nurul Hidayat, and I have an honor of guiding you through today's program. And yesterday, we were inspired by remarkable presentation from our 5 keynote speakers and parallel sessions, presenters. Yesterday, we were inspired by Professor Cheng Hao Chuang from Tamkang University, Taiwan, Dr. Mi Jin Jin from IBS, Institute Basic Science, South Korea, Professor Koji Nakamura from Mi University, Japan, Professor Marcus Diantoro from Universitas Negeri Malang, Indonesia, and Professor Masaki Fujita from Tohoku University, Japan. Ladies and gentlemen, today we have a promise to be equally enriching, as we will have the other 2 distinguished keynote speakers. Those are Associate Professor Warawat Mevesana from Suranare University of Technology, SUT, Thailand. Welcome, Prof, to Malang. And also Associate Professor of Technologies, Dr. Muhammad Safwan bin Abdul Aziz from University Technology, Malaysia, as our remarkable keynote speakers. Today's program will include our plenary sessions and also followed by the parallel sessions. And we will conclude with the closing and awarding ceremony for the best presenters at the end of the program. Ladies and gentlemen, to moderate today's plenary session, we are honored to welcome a distinguished physicist and also one of the Indonesian's leading experts in magnetic materials and superconductors. He completed his bachelor's degree in physics from Universitas Pajajaran in 1998. He then pursued his master's and doctor's programs in applied physics at Waseda University and also Tohoku University, respectively. Following his doctorate, he conducted postdoctoral research from 2008 to 2011 at the prestigious research center that is Riken Nishina Center, Japan. And 10 years ago, he was conferred the title of full professor with a research focus in magnetic materials and superconductors. Ladies and gentlemen, it is our great pleasure to welcome to the podium the moderator of this morning plenary sessions, Professor Dr. Rizdiana. Professor Rizdi, time is yours.
Okay, thank you very much, Dr. Nurul. Good morning, ladies and gentlemen, and keynote speaker, invited speaker. Welcome to our second day of the International Conference on Magnetism and its Application 2026. So we are sure that today we also can get another exciting series, discussion, and insightful presentation, and also hope we can get further collaboration. Okay, first, we are honored to have Professor Muhammad Safwan bin Abdul Aziz from the Ibn Sina Institute of Science and Industrial Research, University Technology Malaysia. Please come forward, Prof. Safwan. And the second keynote speaker, we are also delighted to welcome Professor Warawat Mevesana from School of Physics, Suranare University of Technology, Thailand. Please come forward. Okay. Now the first speaker is Professor Muhammad Safwan bin Abdul Aziz from Ibnu Sina Institute of Science and Industrial Research, University Technology Malaysia. His research contribution in advanced materials and scientific innovation have significantly contributed to development of material science, especially in magnetism research in Malaysia. So first, please welcome to the stage and give us your presentation for about 20 minutes, 20 to 30 minutes, yes, please.
Test. All right. So thank you very much, Professor Rizdiana, for my introduction. And Assalamualaikum warahmatullahi wabarakatuh. And very good morning. So first of all, yang saya hormati Professor Ahmad Taufik as the President of the 4th ICMIA, and Prof. Agung Nugroho as the President of Indonesian Magnetic Society, fellow keynote speakers, invited speakers, participants, and ladies and gentlemen, thank you very much for having me today. So my title of presentation is, as what in the slide, from laser plasma chaos to precision nanostructures by achieving it by magneto-optical control. So allow me to guide you through my slides, which are going to revolve around the very interesting phenomenon of laser material interaction, as well as how does the magnetic field involve in the equation. So my name is Muhammad Safwan bin Abdul Aziz from Laser Center Ibn Sina Institute, UTM. I believe some of you might have come to UTM and very familiar with it. The rest, I will welcome you guys very much to UTM. It's the southern parts of Malaysia. So yeah, can I have the next slide, please? Okay, allow me to start my presentation with a brief introduction of what is actually the phenomenon called plasma. So generally in physics, plasma is regarded as the fourth state of matter. So what does it mean? We have a solid, form of solid, and then we heat it up. We're going to absorb the energy in form of heat, going to start vibration wildly and then turn into liquid. So if we continue to heat up the liquid, it starts to vibrate even more, and then it turns it into a vapor or gas. So what happens is actually gas continue to receive energy in form of heat, so it starts to lose electron. So there we have the fourth state of matter. We have solid, liquid, gas, and then the next phase is plasma. So plasma is actually a combination of a highly ionized gas. We have different species in it. We have a charged particle, a free electron, and then we also have a positive ion in the plume. Okay, so plasma is actually, it's like a shield phase where it comprises of high energy. It can simply reach thousands of Kelvin in terms of the temperature. And then there are lots of physics going on. We have scattering, radiation, collision, inverse Bremsstrahlung, and a lot more. So I would call it as a beautifully chaotic phenomenon that do we actually know the behavior of plasma itself. And if we can govern the plasma, for example, behavior in terms of expansion and collision, can we actually control the plasma? Like how do we control electricity flowing from higher voltage to low voltage? So that's basically the theme of my presentation for today, and it involves the effect of external magnetic field into it. So as you can see from the picture, there are many ways of generating plasma. This one I show in the slide is basically when we hit a laser beam, focus onto a small surface spot of a target, then it quickly vaporizes and turns into plasma. Then we have plasma plume, and then this plasma plume expands so fast that it creates a shockwave front. That's also another interesting thing to study and understand it fundamentally. So can I have next, please? So yeah, without we noticing it, plasma has played a major role in our daily life. If I can name a few, I think plasma has been proven to play a significant role in energy. For example, it has been proven to improve, the oxygen vacancies, basic defects in terms of the electrode that will further convert Hello? Yeah, I'll continue. Higher yield of hydrogen production, in terms of advanced manufacturing, where they are now basically building a 3D metal printing. So if you want to print some structure from polymer or plastic, you can get it very cheaply, 1,000 ringgit. You can get a complete 3D printing setup. But if you're talking about if you want to build a 3D based metal printing, then you need to heat up the powder metal up to a few thousand degrees Celsius. So that can only be achieved by using a focused laser plasma, because we want to print it as small as possible in terms of resolution. So the product, the quality of the final product really depends on how do we control the plasma from the laser interaction. The other thing is basically in biomedicine as well as nanoparticle synthesis by using pulse laser, which I'm going to walk through slowly as we go along in my slide. So next, please. All right, so there are many things governed by plasma without we noticing it, obviously. So in the realm of laser material processing, in which the field I am from, achieving a precision manufacturing actually required a precise control of the plasma behavior. But the only problem is plasma itself is a very chaotic, that involves a lot of multi-dimensional physical phenomenon. We have rapid expansion of the plasma plume, and then there's a turbulence, stochastic cavitation, ultra-fast evolution, that almost everything happens within the plasma plume is not obeying the linear process. It's more like a non-linear interaction between every single species of them. There's a video, I don't know, can you play that? So yeah, that is basically a video of high power laser. All right, never mind. High power laser, 1.5 kilowatt being directed into a metal sample, and yeah, there are absorption, there's scattering, there's a signature, what they call it, emission lines that we can collect and further monitor in terms of its process quality. Now, that brings me here basically. Can the magnetic field provide additional control over the plasma behavior? And if it does, to what extent can we actually control the process? So yeah, I would like to share with our fellow friends over here my field, the experience for the past couple of years I've been working on this. It's very interesting. So next. So before that, allow me to introduce a little bit about my the center which is I'm coming from. It is called Laser Center under University of Technology Malaysia. We own a 5-story building. A quarter of it is located in T05 UTM. If you have anything, you can slide. You can scan the QR code. We can start new collaboration or any potential works together. Next, please. Very quickly. So yeah, this is another aerial view. It's a beautiful place in T05, in southern part of Malaysia. You guys are very much welcome to come and collaborate with us further. Next. Yeah, this basically anything related to laser material interaction. I believe we have done it. Most of them we have from nonlinear optics, laser material interaction effect of magnet and so on. We even produce single crystal trying to produce single crystal for the laser. Heart of lasers itself is basically the crystal. Okay, thank you very much. It's supposed to be playing. All right, this my essence of my presentation today, table of content. I'll guide you through step by step from the mechanism of pulse laser ablation in liquid. Before that, what is that, and then how does the magnetic field actually play a role in that sense, all the way until the impact and future direction. Where do we go from this standpoint? Thank you very much. Next. All right, so pulse laser ablation is what the name suggests. It's actually a method to produce nanoparticles by using intense pulse of laser. You know what happened when we focus a very, very high energy intense beam of laser into a single spot? So the particle, basically, the material on the surface will absorb the energy and straight away vaporize it. It's a very, what they call it, high energy being focused onto a single spot. So what happened actually, this will in turn, liquidify, vaporize, further turn it into a plasma. So the advantage of this method is actually, compared to chemical method, I take some example to Cavish method to produce gold nanoparticles. At the end of the day, we still get nanoparticles of interest, But to get there, along the way, we're going to produce, a lot of byproducts, for example, some toxic or, some byproducts along. So as compared to this method, to start with, we only have deionized water or pure water, and then a sample of gold that we shoot it by using laser. To start with, we have only the energy from the laser, the liquid surrounding, as well as the target metal. So it's most unlikely we're going to have our impurities in our final sample, right? So the process is basically simple. When we deliver a laser on surface, that process is similar to laser engraving, right? Whatever left on top of the surface, you're going to have the engraved surface. But the thing is, we are not really interested on what left, but we are interested on what being ejected out. So this setup is pretty much simple. Whatever ejected out from that plasma, we collect it in the liquid form. So we're going to have colloidal nanoparticle of interest. All right. So in terms of purity, toxicity, flexibility, it has an advantages directly compared to some of the chemical method, but it does not come without any limitation. The main limitation of this process is actually the low production concentration. You need to keep ablating it for hours to achieve some minimal milligram per ml of nanoparticles. And yeah, that's mainly because of the shielding effect, which is I'm going to show it later. Next, please. All right. So yeah, this is the I think basic mechanism or interaction that produce the nanoparticles. All right. So for the first thing, when the light interact with metals, it will be rapid heating, and then there's ejection of atom from that vapor, right? And then the next phase is going into a phase of plasma creation. A very, very dense plasma plume that contain all these species will come together just barely on top of the surface. And then the next phase, it will be plasma expansion. The plasma will have, a very high pressure and temperature. You're going to, expand it throughout the surrounding liquid. And after a few microseconds, it starts to entering the cooling phase. All right. This is where basically the nucleation start to happen. It's very crucial to control this process in order to tailor the properties of the final nanomaterial. Right. And then when the plasma wildly expand into the liquid, it is then definitely create a shock wave, right? And we call it cavitation bubbles, and it start to ablate the particle into the surrounding. And then after series of expansion and collapse, you're going to produce more smaller and stable nanoparticle. So it's basically intricate properties that need to be understood well as we need to be able to have a degree of control if we wish to produce, a good quality or better understanding on how do we produce nanoparticle by using this method. So yeah, next. Okay, this is basically the main challenge within this process. We call it as a shielding effect. Normally, we would use a laser pulse, laser in form of pulse to start ablating. The first pulse will hit 100% of, most majority of its energy towards the point of interest. But the problem is the second pulse, when it tries to reach at the same target, it's not going to behave exactly the same. We start to have a plasma plume. Right, so this plasma ejected from the first pulse of laser will now create shielding. There's nanoparticle cloud revolving around that one. So the energy from the second beam of laser, majority of it will be lost in terms of absorption and scattering, to heat up the nanoparticle that located in this plasma shielding region. Right. So that means the less energy will deliver to the same spot for the twice, third, and the fourth, and so on, number of pulses. So these are the main challenge that limit basically this method to achieve, a better concentration or better output yield. All right. So yeah, laser pulse will create a plasma cloud, a very dense plasma cloud, and the plasma cloud almost acting like its own shield for the next laser beam to be delivered to the same spot. So as a result, the yield will decrease. We're going to have ununiform morphology and size of the nanoparticle, as well as it's going to waste a lot of energy into the surrounding. So that picture over there is basically the expansion of plasma. And the next picture is basically showcasing the next laser pulse is trying to hit the same spot but being blocked. All right. So yeah. So the question over here is basically, can we control or mitigate this challenge or this problem? We can actually do that by involving external control. One of it is through the utilization of external magnetic field. So there are two strategies to achieve that. One is basically the external magnetic field itself will alter the plasma dynamic, the interaction of the species within the plasma plume, right? And I'll get that through as we go along. And the second strategy is basically how does this shockwave cavitation bubbles govern under the external magnetic field, all right? So yeah, in that case, it's what again bring me here. I would like to share a very interesting phenomenon when we have a laser interacting with metal with and without the influence of external magnetic field. It shows a very, very wide difference between the results and quite an improvement actually. All right, next please. Okay, I actually cannot read it from there. So, first of all, the picture on the right, when we have a laser exactly, focus on spot of our sample, metal, for example, at the same time we can use basically a permanent magnet, or we can use electromagnet to introduce external magnetic field into the point of interaction. So what do we have at the end of the day? So we know that basically, I think yesterday Pak Taufik asked us to make this sign, Lorentz force. So when we know that our plasma will have a charged particle, we have external field, a moving charged particle under external magnetic field, we're going to start to observe a Lorentz force, all right? And then, so what does it do? So when the charged particle basically moving in this direction, and then we have control magnetic field in another direction, we start to deflect it towards by using Fleming right-hand rules, right? So if the particle movement is not exactly perpendicular with the surface, it's starting to make a circular motion or almost like a helical motion, all right? So the electrons, the charged electron and ion will eventually rotate around the magnetic field line, and their motion becomes confined. Because in the conventional pulse laser ablation method, the plasma is basically freely, almost no restriction. It can expand in whatever direction they wish, right? But under the external magnetic field, actually we govern their trajectory so that they revolve around the magnetic field in such a way that we call it as a magnetic confinement. So what does this magnetic confinement actually do to alter the properties of its final product? It's actually when we have a controlled trajectories of plasma species ejection, we're going to have increased plasma density. And this plasma density will later, produce, increased plasma lifetime, stay there longer. So when plasma lifetime increase, we have a collision frequency increase, and this will in return produce a better nucleation condition, and then further improve the growth. We say that we managed to somehow have a degree of control on the nucleation process until the nanoparticle is being formed, right? So in that sense, we can actually alter the properties in terms of its crystallinity, modify its defect densities, oxygen vacancies, and improve nanoparticles yield at the end of the day. So if you can see from that picture down there, the heat contour one, so it's simple, that is basically plasma under the IR camera. So from left to right, I don't know if you can see through the resolution, that is basically a size of plasma under external magnetic field, but we keep on increasing the magnitude of the magnetic field from 0.1 to 0.5 Tesla. So as you can see, the first one, the plasma is actually, as we keep on increasing the magnetic field, it starts to confine this charged species. So the size of the plasma plume is, I think, significantly smaller, and also the lifetime will stay longer. This is exactly what we managed to observe under the controlled environment by using external magnetic field. All right, so that is basically the first strategies. And the second one, please. Next. Yeah, I think you better look over there. So after this series of plasma expansion, there's another interesting phenomenon that will eventually occur right after that. It's basically a shock wave formation. You know, yeah, that picture on the right, we did that experiment I think a few years back. If you look carefully, if the resolution is better, we can actually see a shock wave front, you know, associated with that frame rate after few nanoseconds. Right, so the first few nanoseconds, we call it onset, you know, the plasma start to create, start to originate, and then after around 10 to 100 nanoseconds, we call it detachment, the particles start to ablating out, and then the shock wave will eventually form after that. So the thing is, when the shock wave being expand, it will eventually not stay at a state for long. They're going to collapse back because of the pressure from the surrounding liquid. So when it collapses, it compresses back all this nanoparticle into a single spot. So it will be bouncing back, and further we can observe, you know, a series of what you call it, cavitation bubble formation. It's basically a series of plasma expansion and collapse, expansion and collapse. But interesting thing is, after series of expansion and collapse, we're going to observe that each oscillation becomes smaller, weaker, and then you know, slower until it finally disappears into the surrounding liquid. That is supposed to be a video. I don't know. Can you play the video? Actually, it's a very interesting video. I don't think so, because this is, I think, flattened PDF. All right. Okay. Never mind. I take a video of the plasma expansions and you know, corresponding to its shock wave with and without magnetic field influence under the high frame rate. Video is 1/1,000,000 frame per second. But anyway, that's okay. We will not be able to play that. All right, never mind. I have another better image that I plotted basically in the next slide. So yeah, next slide, please. So what happened, this one on the left is basically without the external magnetic field. The one on the right is the frame rate with magnetic field. So because it's, I want to show the straight line, so I plotted this we start from 2.28 microsecond, and then, what is that? I also cannot read it. Then few microseconds after that. So without basically magnetic field, the plasma expansion and collapse, they're going to start that similar process exactly at the same point. I draw it as a straight line over there. So interestingly, under magnetic field, you know, because when the plasma expand and collapse, we control the charged particle trajectories. So when they expand and trying to collapse, there's a skew in terms of the density of the charged particle closer to its magnetic field. So this will in turn shift the center of expansion for the next consequences. Next consequence, plasma expansion slightly skewed to the direction of the magnetic field. So why does this phenomenon matters actually? So that will, and we know when you shift the center of the plasma, that causes shielding effect towards the other region, the next beam of laser can hit with almost full of its energy fresh on top of the new surface. So that's how we actually control and make sure that the interaction between laser and matter throughout the process is uniform. All right. So yeah, magnetic field induce bubble asymmetry and reduce plasma shielding effect, and this will enhance, you know, more effective laser target interaction and you know, translated into better properties of the nanoparticle at the end of the day. Next. So these are basically a simple setup. In my lab, you guys are basically welcome to come and visit for any sort of collaboration. We use fiber laser source, right? And then we actually control the beam of laser, the guided beam of laser by using galvo mirrors. And then there's our sample in the cuvette, and then we put a magnet. In our case, we use a permanent magnet. We somehow managed to control the distance between them to get different magnetic field strength. In this case, we use ferrum and an iron target to start with this high purity iron target with deionized water. Our laser is pretty much not at high energy, only 18 watt, 20 kilohertz of frequencies. And then we have this magnetic field we varied to show the proof of concept from 0 up to 150 millitesla. Yeah, next. So these are simple results. I think I go through very quickly. So under different strength of magnetic field, we actually get the absorption of the ferrum oxide species that we produce with higher concentration, right? So we plot the concentration by using this distillation method. At the end of the day, as we keep on increasing the influence of magnetic field strength, we're going to have a better concentration of this, in this case, is ferrum nanoparticles with different species, all right? And then as well as it somehow slightly alter the band gap. I'm going through this very quickly. And also, this is very interesting. We somehow managed to prove that this controlled plasma phenomenon, we can actually introduce more, defects. And then by controlling this defect and oxygen vacancy state, we can actually say that we can tailor the functionality of our nanoparticle of interest at the end of the day. Next. All right, this is another result. I think we did it briefly just to prove the concept, basically. And yeah, through the XRD and then followed up by TEM, we somehow managed to get iron metal nanoparticle, as well as another species is alpha hematite. Right? Maybe if we can control the oxidation environment better, we will eventually get magnetite instead of hematite. So I go through this one very quickly. Thank you. Thank you. Next. All right, so I almost finished my slide, basically. So why does it actually matter? In the realm of laser plating, laser engraving, metal printing, and so on, they normally have this monitoring system. A big main player in this industry, Renashaw 3D System, X1 company, many Western companies are basically having this AI control of the quality. So, but majority of them can only monitor the quality of the printed part right after it has been printed out. So actually by understanding and having somehow controlling the plasma behavior, we can actually tune or control the process not after the product has been done, but before. That's where the science, that's where the interaction happened at the first place. These are series of, the technology they are basically bangunkan, yeah? They are promoting, but they still somehow have a pro and cons between them. So that's why it is basically important to understand, and the way to do it is basically by carefully controlling this effect of magnetic field. So that pretty much the essence of our presentation today. I think with that, I thank you very much for your attention. I leave it back to Prof. Rizdiana. Thank you very much.
Thank you very much, Prof. Safwan. This is very interesting talk. So we can control a lot of parameters using the pulse laser ablation. So, okay, we will have a discussion after Professor Wirawat's presentation. Okay. Okay, we welcome Professor Wirawat Mepesana from the School of Physics, Suranare University of Technology, Thailand. His expertise in condensed matter physics and low-dimensional quantum material has made important impact in the field of modern physics and spin-related phenomena. Please welcome Professor Wirawat. Time is yours. Give applause to Professor Wirawat.
Thank you very much for the introduction, and also it's very nice to be back Malang. Every time that I come back, feel like home now. So yeah, so yes, the slide is up now. Okay, so yeah, today I will talk about a bit about the magnetism that you ferromagnetism that you can find in carbon. So this is something that we did not expect to see this, but we're going to share this later on. Yeah. So my name Warawat Miwasana from SUT, and also another organization that we are doing now is called QTRIC, QTRIC. That's the consortium that we are building. So hopefully we can introduce you a little bit about that as well. Yeah. The next slide, please. And then before the letter of my talk, these are the students that I had. So yeah, many funding that we got supported by, and also the student who it's a bit hard to see in this picture, but yeah, there's at least 4 students that I'm gonna show the data later on. Is Sumed, and also the Sujinda, and also the Supanat, and also Seksan. Yeah, so these are at least the 4 students that in this picture that who help doing the work that I will show you later. Yeah. Next slide, please. Yeah, so the first I was asked that if I can give the introduction a little bit about Qtrix, which is not the main talk, but I guess I hope that maybe this is something that we are pushing very hard, and hopefully we can have more collaboration on this movement of quantum tech in Thailand. Okay, so the Qtrix stands for the Quantum Technology Research Initiative Consortium in Thailand. So we have about 19 organizations in this from mostly university and also like institute, research institute, and also 2 startups that in this team, big team that got support by the Ministry of Science and Higher Education. So agency called PMUB. Yeah. Please, next. Yeah, so if a little bit of the motivation, if you may have heard already, so when we talk about quantum, so we mostly think about the quantum computer now. So back in like 2019 or so, Google has announced that there's the thing that called quantum supremacy, which is if you select one problem that and compete with the digital computer that the best. So that in that case is a random quantum random circuit that was tested back then. The task of calculation is not something useful, but at least it shows that quantum computer can beat the classical computer by far. So that's something that we kind of think what's going to happen next. And then when I talk about quantum technology now, it's not just the single technology anymore, but more like the era that we come. So if not it's probably hard to imagine what is the era of quantum will be like. But if you could look backward, actually it's quite interesting that we had this kind of thing before, like the change from analog to digital era that we are in now, that many things have changed, and we also have the term like digital economy. So economy really changed because like for example, like e-commerce, and then things are got very faster, like the mail was sent by email, for example, and we have talk Zoom and things, etc. The cost of many things are very different, and then if you have to use it, then quantum will come again. I think this is the kind of era. Next slide, please. Yeah, and in Thailand we have developed this kind of roadmap, and also set up many things from back in 2019 or so. Yeah, so that kind of starting of our consortium. So we start from many topics, so quantum sensing, quantum methodology, quantum communication, quantum computing. So these are more like the bigger picture of quantum technology in Thailand. This is a bit out of date now, but it's original roadmap that we had back then. Yeah. Continue, please. Yeah. So a few more slides on the quantum Qtrix is that right now we work as a big consortium. So quantum, how to use is this also feel free to share, and so hopefully if you are interested in this, we can like control many things now. So like single ion, single atoms, single molecule, and also like entangled photons for communication. We also have some applications already in magnetic sensing and also quantum sensing for detect disease, and also magnetic sensor that I will show you a little bit on. Yeah, and then some quantum algorithm. So this is like the map of Thailand that we work closely together. This is some event that we organized last year, and also I just finished the event in Thailand just yesterday. So just through it, so I come a bit late. But this is a picture of like some of the event that. Also, the next one, please. Yeah, so some of these maybe would like to invite like many students who are interested in quantum technology. So we probably organize this from time to time, and so we welcome like ASEAN students. So last year we have about 300 applicants from ASEAN. So from Thailand only about 50. So like ready to 50 from abroad. So this is some of the friends that we also organize together in back in then. Yeah. So that's some stat of the, we have published some paper, not a lot, but I mean some of them is in good journal, like from the team, like Science and Nature. And yeah, continue please. Yeah. So we have about 120 members in the group, and one of the things, I will not go into detail, but like quantum sensing will relate to the magnetic, that the topic of this one. So I just pick only one that relate to this. Continue, please. Yeah, continue, please. Yeah, so one of the things that I try to choose and talk to is carbon at the beginning. One of the carbon is diamond. So diamond can be very useful for to make quantum bit. You can make quantum bit from the nitrogen vacancy in this diamond. So the color is not going to be clear, but it's going to be some color on it. And you can detect like each vacancy, and you can use that as the qubit. But at the same time, you can use that as the magnetic sensor. So the next one, please. So some of the, next slide, please. Yeah, so one of the things that because the quantum bit usually is very sensitive to extra environment around it. So one of the things that can sense is a magnetic field. So one of these is could be very useful, and if you can see that, I mean, this magnetic sensing is only one atom, so you can put as many as you like into the system. And this is maybe something that could be complementary, or like medical imaging that can be complementary to MRI, for example. So this is the thing that we have done, for example, but there's a lot more in the team, but we're not just to talk on that. So I will switch the mode now, so I will come back to what I have worked on that relate to this and also relate to carbon. Next, please. Yeah, so this is my actual outline of the talk. So it was given the introduction to the Q-trick and my things. So the title of my talk today is a tunable ferromagnetism in CBD synthesis carbon films. So in this one, we want to go a little bit on this direction that from the material that I will introduce you to the diamond dots, and then so on. Next one is just a quick motivation that why we can observe the magnetism in this diamondoid film, and then so the ferromagnetism that can be observed very clearly, very strongly, and then also we're going to discuss about the effect, how the origin of this effect. So like the dangling model, and also like some experiment that they're going to show is the EDS experiment, Raman, and MFM, this is a magnetic force microscope, and also the application that you can enhance this a lot by exploration, just very simple technique, and also like the more advanced one is like electron beam lithography patterning. So they can boost the magnetism quite a lot more. Yeah. So yeah, go to the next one, the introduction to the diamondoid, please. Yeah, diamondoid is it's the same as diamond, but it's just small molecule. Is the smallest one is a C10H16 adamantane. So it's just the sp3, like the big, and then you can go up higher and higher. So the first two, I think you can synthesize it okay, but if the higher molecule is usually in the petroleum, so you can sometime in the pipeline of the petroleum there's something stuck, like in Chevron they find this in the scrap around this the pipe, the oil pipe, and then they can synthesize this more, the higher molecule. I mean, the extract, not synthesis. They can extract more on the higher molecule. So, but we're going to focus on only small one. But the higher one is something that about diamond. Next, please. So, if you not already know, diamond is actually quite interesting. Not just it's expensive, right? You can use for the diamond ring for your wife, but also it's very strong. Very hardness is very high, but also in electronically, diamond can be superconductor as well if you dope the surface with it. And also another one is the diamond can be emit electron very efficiently, can emit electron out because the negative electron affinity. So you can use this, but diamond is expensive. You're not going to use for the device much, but diamond door is not expensive. So we thought back then in 2007, many years ago, almost 21 years ago, right? Almost 20 years ago, sorry, 19 years ago. Yeah, so we published this in Science, and I'm not just the co-author, but then you can find that diamond dye can emit a lot of electron from this. If you play it well, you can coat it with something. And smaller one as well, not just the bigger molecule, like the adamantane. These are the things that got interested at the beginning. Yeah, continue, please. Yeah, another one that related to maybe some of interest that I find it in Malang. So when we thought for a while, I mean, we know this for a while, and we thought, what can we use it for? One of the things that we just realized that we can also use for enhance like solar cell as well, because if you excited with the light, it emits a lot of electron out. So you can use that diamond dye electrode to boost the electron emission. So you can boost the efficiency of the solar cell. Like this one is a DSSC, so dye-synthesized solar cell that you can boost. For example, like as a reference, like if you use the platinum electrode, you can get 9%, but if you use diamond dye electrode, just change everything the same, you can boost to 11%, almost 12% or so. So this is what excited us at the beginning at that time. I'm not the expert in the magnetism, but we started to slowly get interested because the next talk. So one of the students that, master student, so this is the thing I would like to share to the student, especially the student as well. So we had dinner last night, and then some of the common talk would be that, oh, okay, I planned many things so well, but somehow the result does not come as I expected. So I said to her that this actually could be a good opportunity. You can find something, maybe you have a chance to find something new that not, usually for my, if everything go as planned, it's kind of boring, and so you get published and think you can finish, but it's not quite interesting things. So this one, same guy, my student, so one of the students, yeah, he worked to try to make electrode for the solar cell, but with different technique. He want to do CVD to use as a solar cell. Did not go so well, but he had a lot of sample already. So one day, next slide please. So one day there's a talk by like this that I'm across the field. So I'm not in, as I mentioned, I'm not in the field of magnetism, but I go to listen anyway, and then I find there's this one professor, Professor Supri from Konkan University, that Professor could planned to go earlier. But, yeah, so he gave a talk about this magnetism in carbon. So next slide, please. So he said this, tell us the story about this, that you can find, not his work, but he just in the introduction that you can find the ferromagnetism in Teflon. Teflon is like the plastic sheet that you can use for, it's a branding, right? Copyright names, Teflon. If you just kind of tear it, like make it apart or destroy it, like tear each one, the magnetism go up. You can measure it, but it in order of milli EMU per gram or so. It's not a lot, not very high, but the more you destroy it, the higher magnetism you find in this one. So actually, I will explain a bit later on. It's related to dangling bond of the carbon. If the carbon has a broken bond of something, and this bond is aligning in a way that constructively, then it can enhance the ferromagnetism in carbon, which is usually take it as a non-magnetic element. Right? So this is a thing that got excited. We got excited to listen to this talk, and then as again, my student who worked very hard on the solar cell part, but could not find something new, so he has a lot of samples. So I just say, okay, you go to measure magnetism in that film, because usually the diamond dye you do CVD, you broken the bonds, and you see if they can find something new. So yeah, that's come to the later part. So observation of this ferromagnetism in CVD carbon film. So next, please. Yeah, so what he did, as I mentioned earlier, so he planned to use this as for the solar cell electrode, but he has not very successful in make a high efficiency. So he basically what we do is that the CVD is you can put the vapor of adamantane, you can heat it to about 100 or so, it become vaporized, and then you can put in a CVD. The target is in the main chamber. The temperature around probably around 1,000 Celsius, or maybe could be a bit higher, like 50 degrees Celsius. And then the adamantane that get vaporized will go there, and then the bond breaking there, and then change from the clear color to the black one. Okay, next slide, please. So you can, these are the substrate. We can use different substrate as well, but the one that easiest for us is just use quartz substrate. So the initial one is just clear. You put S underneath it just to the letter so that you can see the difference. So after you put the CVD, create the film, it can become somewhat black. So I just joking with, at least if you don't publish in other things, you can use maybe for the sunglasses. that's actually very, very tough as well, very strong. Yeah. And next, please. Yeah, so you can characterize it a little bit. So the film that we use for this discussion is the thickness is around 1 to 1.5 micron or so. You can tell from the I think this SEM, right? Okay, and then you can check and other thing like Raman spectroscopy. So we can see that, I mean, diamond dye itself should be sp3 100%, but after the CVD process, some of them become the like graphite-like, so that you have to peak, D peak and G peak. So that's the two. So so this ratio we're gonna discuss a bit later on, but it's not. I mean, the bond is breaking in the process. Okay. Next, please. Yeah. So yeah, this is come as a surprise, but not so surprised in the sense that we just keep measuring. So he got excited. My student went alone, and then he showed the result that he actually find the carbon, the ash-grown, the fresh sample show a little bit of interesting shape like this on just the quartz is the black line, but then this is a VSM measurement, vibrating magnetometer. So and then if you use the ash-grown that you put the CVD of the carbon, you see the red line. And this can be measured at different temperature from the room to go lowest to the 50 Kelvin. So it's more or less stay there. And you can see a little bit of the loop in small, not so big. So it's quite soft magnetics, but you can see it's quite strong. And not just one sample, many samples you can see in the variation of this. So this is, get now excited to see this. Next, please. So, and even more exciting, so as we know, we like to play, so we use the quartz, more expensive, but then we find that there's some construction close by, we just put, steal some small sand from the construction and just make a very small powder, do the same process with the CVD. So this is not, we can play. And then actually, quite surprising, it's not that weak, it's very strong. So you can coat the sand, just the normal sand, construction sand, and then coat it with this diamondoid film. You can use the neodymium magnet to lift it up quite, you can see quite clearly from the picture. This is the original one. So we estimate that maybe this is not weak, so at least maybe close to 1% or 2% of the comparable to like the iron powder. So it's not weak like the Teflon. Teflon you can probably not use the magnet to lift it up, but the sand you can. Yeah. Next, please. Yeah. So then we investigate more. Okay, and try to understand. And I mean, but the direction is already set by us. So we have the model of this dangling bond. So can we test it more to see how consistent if everything go together as we thought it should be? So we have measured some of the EDS and then Raman and also MFM. So this is become our fun toy now. So we just play around with on the line. Yeah. Next, please. Yeah. So first thing before we get too excited, so we need to check. It's not something trivial. So something that we measure is just first thing. Is there any magnetic impurity that can explain this? So just the common one, we just do EDS, and then just check like the iron, cobalt, and nickel, is there any impurity in it? So we estimate this, that we can check all the point, I mean we can look at the SEM in each spot. So if you in the substrate, you just, is one thing, and then the film just carbon mostly. Next, please. And we check that if we estimate, because we know the rough magnetic moment already, so we should know that if something that can explain this, it should be in order about 1% of like the impurity of the iron, for example. So it turned out, I mean, this is, so and our machine is 0.1% of accuracy. So if there's anything that above 0.1%, we should see it. And if it's 10 times, we should really can see it. But nothing is shown. So no other magnetic impurity that we can find detect easily in 1%, that order. So that at least maybe point up to more motivation to try more things. Yeah. Next, please. Okay, so let me explain a little bit more in this one. So this is back in 2003. This is the work that people have worked on, like the buckyball, and then you can break it. You can, if you break in along one direction, it's become like the anti-ferromagnetism. But if you break another direction, that the dangling bond is in the aligned constructively, you become ferromagnetism. So this is a thing that we think, oh, okay, if people find this already, let's play more on our sample. So if there's a way that if you can align it better and how to make it more dangling bond. So we thought of two things. So alignment is one thing, and another one is how can we produce more dangling bond in our film to see if the magnetism can go up. Okay, next please. Yeah, so and then this is the bond that, I mean, just the thought experiment, like what can be the direction of, like, for example, like diamondoid is a C10H16, so that the one cage of this compound, once you put in the CVD, something probably break, because we see that already the sp3 turned to be sp2, some of the compound. Yeah. Next, please. Yeah, so and then we can also test it away with the Raman on the film that we test. So one thing that we play, so if we can increase or decrease this, so we just, this again, my student love it, I mean, because whatever we can find in the lab, we can just use this. One thing we can put is that we just boil it, I mean, put the film in the water and just boil it and see if anything can destroy this dangling bond. Maybe magnetism will go down. So the next slide, please. Yeah, so this turned out that it actually can, if you boil the film a little bit, the magnetism go down. And we can just measure the Raman again and see if the two peak, the ratio between the the sp2 and sp3 band different. It actually go together. Every time you see the magnetism go down, the ratio between the two go down as well. And then we can anneal it, okay. After boil it, just anneal it and then see if they can create more dangling bond, it go up, and then the ratio go up again. So this is seem to be like we come to the right, good direction that probably something related to the dangling bond because sp2 and sp3 has the different chance of the create dangling bond. Yeah. So this is the thing that, and then we can do more. Now we know if we come to the right track, we just keep pushing. If we can increase it a lot higher. So one thing that simple is like we look in the graphene, right? We heard a lot about exploration, so why not just try? We have a Scotch tape in the lab. We just, okay, have the film and you can be Scotch tape it and then hopefully something break and then you create this more dangling bond. Actually, it can, and then we can also measure with the MFM, the part that got exfoliated, the magnetism go up. And that you can prove by the step. You can look at the step from the topography from AFM mode, just normal mode, and you can look in the magnetic mode, and you see that the part that got lift off become shallower. That part had higher magnetism along the way. Yeah. So this is fun, and then we just do the next slide, please. So we create this enhancement or evaluation. So next, please. Yeah, so as the thing that we come to the direction, once you understand the direction is more or less kind of in our control, but not fully, but kind of in a way. So you can evaluate it and the magnetism go up and up and up, at least 2 times. After 2 times, the magnetism go up and eventually come down because maybe we just destroy all of them. The material may be gone or something, so it come down again. But at least we can go up, start from like 0.5 EMU per cubic centimeters, and it go up to about 4 EMU per cubic centimeters, and then come down after that. Yeah. The next, please. So yeah, and then now after some time, the first guy already graduated from done with so many work. So the next guy come maybe can be torture the film a little bit more. So the idea we have more access to the better system as well. We can do lithography patterns. So this is the thing. I hope that if you can create the pattern, maybe along the edge, you can have more of this dangling bond more effectively, and the more circumference around the pattern, probably the higher the magnetism that you can find. So we had created 2 patterns. So one is just a square pattern, but one is about 5 micron, and another one is 20 micron, like just the hair. Not so small, but small enough so you can do this. Next, please. Yeah, and again, this is also, we are happy that it actually can boost quite a lot. So just the normal film that just now, we have about 4 EMU per cubic centimeter. If you do a pattern of the similar film, like the 20 micron, you can go up to 30 something, and then to the 5 micron, you can go up to about 55 EMU per cubic centimeter. So like 12 times become higher from the original film that we got earlier. Yeah. So this is something that, and again, we can just measure with the MFM. Next slide, please. Yeah, and we can check this. So like the pattern, we can see that this is compared between the 2, like 5 micron and then the 20 micron. So the 20 micron, the 5 micron, you can see a bit more signature that along the edge, it seems to be like more dangling bond. That maybe the edge has a higher of the magnetism around the edge of this pattern. So this is something that we done, and I think we, run out of time. Okay, the last slide of my summary. Okay. So yeah, just to conclude my talk, so we can see the magnetism in the CVD that use the adamantane as a precursor. We can check that this ferromagnetism that probably can support very well with the dangling bond model, and can, with the EDS, Raman, and MFM measurement that support this. And we also cool part is that we can control, we can increase the magnetism from the exploration or the EBL patterning this up from like 0.5 MU per cubic centimeter to like 55 MU per cubic centimeters. And then last slide, next one, the last one now. Next slide, please. Yeah, and then just the future work that maybe these are the thing that to think more if you can use, because carbon is biocompatible, maybe we can use for something that in medical or something as, or like the mass production, because it's very cheap. You can make maybe magnetic sand in a big amount that we talk a little bit about the cement company that had a lot of heat. You can maybe put some reaction there. And another thing is not related to magnetism, but like graphene, you can make patterning. You can change the electronic property as well. You can create a gap in it. Maybe that can be related to like terahertz device that in the airline company that you can use for the graphene, carbon metal. Yeah. So that should be conclude my talk, and then thank you for your attention. Yeah.
Okay, thank you, Professor Urat. It's very interesting talk. How to develop and enhance of room temperature ferromagnetism in carbon film synthesized via CPD. Okay, it's time to discuss any comment or question, please. So we already have two, three, four students. It's great. Okay, could you please? Yes, please.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Thank you so much for both presenter. It's very insightful presentations, so I get some information from your presentation. Thank you so much. First of all, actually I have a question for Professor Sofwan. So Prof, basically I was working with the electrode, so too I'm not working in the magnetic material, but I was working in the electrode for supercapacitor or electrocatalyst, something like this. And one of my work was using the laser to modify this electrode. And at the time, I was using the ND-Wave IAG laser with the power output of, I think, about 3 watt to modify the surface. So I could introduce some kind of carboxylic group on the surface of my electrode. So with your plasma laser, is there any possibility to improve, or we can say to modify this kind of surface in such way, like the main properties that I want to improve is the diffusivity, because basically I want this electrode to be able to diffuse the ion in the aqueous electrolyte. So hopefully you could answer my question. Thank you so much.
Okay. It's okay? Yeah.
Okay, yeah, thank you very much for that question. So that is basically pretty much we have done that before. So what do you require is basically they call it laser surface texturing, right? So instead of I'm not sure what type of electrode you're using, but I believe it's a type of metal. So instead of you having a flat and a uniform surface, you know, if you interact it with laser, but it's not just a single spot, it's a scanning type of laser, okay, you can actually control how do you want the surface to be, what they call it, uneven, right? So by using control surface texturing, you can actually alter the properties of the surface of your electrode, right? So in another case, there's another thing could maybe quite similar to what you've been doing. We call it laser surface alloying, right? Instead of that single metal, you're going to paste it with another type of functional material, and then you can basically scribe the pattern on top of your electrode, so that it's totally changed the properties of the material. And you can also try basically. You are using NDX laser, I believe it's a pulse laser. Right? There's another type of laser based on gas, CO2 laser. That's basically very good interaction, interacting with, vast types of metal. So that enhances the absorption. So when the absorption happens, they will, basically alter the properties, the surface properties of your electrode. yeah, you can try that. I think the keyword is basically laser scribing for changing the surface properties of your electrode, and that I think that will help in optimizing the diffusion rate on the surface of your. You're doing electrochemical, right? Electrochemical. All right. I think I answer your question. Maybe we can further discuss it later, hopefully.
Yeah.
Thank you.
Okay. Thank you very much, Professor Fan. Yes, Prof. Eddie.
Okay, thank you. My question to Professor Morawat. Yeah, thank you very much for the nice talk. I think you showed the magnetic properties of the pattern films. So, could you explain the mechanism that you modify the size, you obtain the magnetization modification, and what do you expect if you modify the size into the nanometer scale size and also modification of shape? Thank you.
Yeah. Okay, so yeah, thank you for the question. Yeah. So I think the idea is come from really original from the Teflon. I mean, the more you kind of break it, you create more dangling bond, the chance of more dangling bond. That's the first part. The second part is that you need to align it as well. If you go in the opposite direction, it may be cancelled out. So that, I mean, the first of the reason that you have it on the film, because it probably have a higher chance that this may be more aligned. And then the more you destroy it in a constructive way, then you have a better chance. So I think in my slide, I think the 5 micron pattern, you can see that the edge probably seems to be more like from the MFM to be more magnetic moment along the edge. So that may be help to increase. So I guess, I think we cannot try more, but I mean, if you make it smaller, I think you can have, but until you probably hit some problem with other problem, maybe gonna come down again. But at some point, I think we keep going if you make a smaller pattern. Yeah.
Okay, thank you. Okay, we still have two. Yes, please in the.
Okay, let me introduce myself. My name is Latifatul Aisyah Nabila, and my question is addressed to Professor Safwan. In my research, I also frequently use the laser ablation method in material synthesis, and I would like to ask if this experiment were conducted without a liquid medium, such as in a gas environment or vacuum, would the magnetic field still have a significant influence on the plasma compared to the liquid condition that involves cavitation bubble and shockwave dynamics? And the next question, since the presentation used Fa as a ferromagnetic target, could this experimental setup also be effectively applied to non-magnetic, such as gold or silver? And would the magnetic confinement effects as well as the resulting nanoparticles characteristic differ significantly? Thank you.
Okay.
So,
you
thank
can
you.
get your.
All right, thank you very much, Aisyah Nabila. Yeah. So that's good to know that you are basically working on pulse laser ablation. So yeah, the concept is like this. First of all, if you are not using it within the liquid, then we will call it pulse laser ablation deposition, right? So what differ me from your setup is basically whatever ablate from this interaction, that laser work almost like a palu, yeah, almost like a hammer palu. So we interested on what is basically being ablated out. So if you are basically immerse it within the liquid, so whatever coming out will quickly being captured in the liquid solution. So you will quickly get a colloidal, right? So that's what we have been presenting just now. So if it's not, then there's another technique that's quite common. Basically, they put another substrate behind, right on top, close to the vicinity of that target you ablate. So what happened, basically, the ablated particle will form a deposit. You can control it and it turns into a thin film. Right, the question is, normally you would need to do that within a vacuum. you don't want this plasma that has an ion, then electron or not a neutral particle be colliding with the molecule in the air. So first of all, you can control it more if using it in a vacuum. So it will actually be governed by the same exact mechanism, because it's, whatever metal it is, after it's losing its electron, they're going to have to ion. So when you have a magnetic field, we have a Lorentz force acting on the charged particle, you can actually control the trajectories of how the particle accelerate. Yeah, you can do that. The second question is basically if you're not using a ferrum, ferrum will eventually produce a magnetic nanoparticle. So that's the same concept. If you, I did it with, I think pretty much different types of metal, nickel, gold, for example, right? As long as you have the energy high enough, you can create this ionized gas, then you're going to observe this scattering, electron trajection, you have this inverse Bremsstrahlung, energy loss. But you, at the end of the day, you have ion. Ion can still be governed by that physics law where you can actually alter the trajectories, all right? So on top of that, you can also couple it with not just magnetic field, you can also, connect it to the power supply, that different voltage will further accelerate the electron. So by intrinsically balance out within this voltage difference as well as this external magnetic field magnitude, you can actually deposit it. You can actually produce the nanoparticles quite evenly, and with a better improved performance. I think that's my suggestion, Nabila. Thank you.
Okay, thank you, Professor Vance. So the last, yeah, please.
Okay, let me introduce first. My name is Diana Regita Yuning Tias. Continuing Nabila questions. This research for lesion ablation use magnetic field to ensure the result were homogeneous. However, in other research, use rotating device to homogenize the nanoparticles. So, which one more effective, both of the methods?
What is the other device you say?
Rotating alat.
You are basically targeting the laser on top of the surface on the spot. At the same time, you are rotating the sample.
Yes.
Yeah, all right. So that's the beautiful thing about this. There are few strategies, all right. The reason people would normally rotating the sample is you want to have a fresh surface every time you interact with lasers, right? So if laser is like this, every time you interact, you're going to ablate some mass out, you're going to have different level of focus. This table, for example, you hit it once, it's flat. You hit it after 10 times, it's getting down on the surface, right, a little bit. So that will actually alter how precise laser it will alter basically the properties. So every time when you rotate it, you're going to have fresh particle every time. But again, it depends on this, how fast you rotate it, how quickly your ultra-short pulse laser is. You still suffer from this, shielding effect if you're not rotating it as quick as possible. So that is one of the strategy. But if you can further couple it with what basically I mentioned just now, I believe you get a better result. At the end of the day, it's the same. We want to run away or mitigate these shielding effects, right? Then another method where basically people are using, instead of rotating it, they keep flowing the fluid. Instead of a static in the cuvette, you have this parallel static pump going around. That will also help. It is proven method that you can test. You get more homogeneous sample at the end of the day. So that helps, but try to couple it with another factor. I think magnetic field is the best way to actually control it. Yeah, makasih.
Okay. I think we still have a short question. Yeah, please.
Okay, thank you so much for the opportunity. I have a question for Associate Prof. Worawat. Okay, on your presentation, I'm really curious about the big picture of your materials because you started the presentation by framing the shift from digital to quantum computing. In your opinion, will diamond-based materials like the one you research play bigger role as hardware component inside future quantum computers? So, or as external quantum sensor like the NV magnetometers used to test them of computers quantum? Thank you.
Okay, so I think there's two separate parts. So the diamond dye is a smaller molecule, so maybe that can be used for like materials, quantum materials for making some device or some other things. For the quantum sensing, the diamond, that's maybe more the normal one, but you use to implant something. That one, I think that at least that one would be have a big application later on. I'm quite sure. So like if I explain in that the first bit, I did not talk much on the first part. So it could be initially it can be used for making qubit, quantum bit, but that is not going to be scalable easily. Some company can be scaled up for the quantum computer, but that's probably not the direction it is. But quantum sensing, there's a lot more opportunity. So one is for imaging in medical imaging, because it's only single sensor. So maybe if I try to be more fancy, more sci-fi, like the futuristic. So like if you know, like the people has done some brainwave before, right? You have sensor on your head and you can like a Stanford research. You can speak from your mind, right? You don't need to type, and you can, but it's slow, like 15 words a minute or something like that. That's the thing. But later on, if that's only like 20 or 40 sensor around your head, but if you have like only one single atom sensor, you can put as many as you like around your head, and that's going to be more. But that's going to be take quite a while. But I'm sure that maybe some projection in that one. That's more futuristic, but more like closer one. Another one that could be used is a magnetic sensing that especially related to this community. That diamond NV center, you can use as a magnetic sensing that for navigation. So as you know that in the current state there are so many wars around the world. One thing that could be hurt us is that the GPS jamming can be done actually quite easy. The GPS is very expensive technology, but you can jam it maybe with very cheap jammer. You can destroy it already. So that navigation maybe need to have a second like technology that support NV center navigation that can detect the Earth magnetic field. You can map to the location as well. That's another thing that people are discussing, and I think that could be the closer like application that we may see in 5 to 10 years in the market. Yeah.
Okay, thank you very much. I think time is up. We can still have time till noon for discussion with Professor Sofwan and Professor Wirawat, also with other keynote speaker. Please give our warmest and big applause to Professor Sofwan and Professor Wirawat. Thank you very much. And also, this is the end of our all keynote speaker session. Actually, we still have a plan parallel session and also coffee break. The coffee break is in the right side, and then the parallel session will start from 9:40. Yes, we still have 8 minutes to take a coffee. Okay, thank you very much for all participants and all keynote speakers. Thank you.
cek pengumuman sebentar. Bapak, Ibu, dan teman-teman presenter yang masih ada di luar ruangan, mohon untuk segera memasuki ruang-ruang sesi paralel, mengingat hari ini juga adalah hari Jumat dan nanti kita ada closing ceremony supaya waktu kita tepat waktu. Terima kasih. Oke, Bapak Ibu semua, mari kita kembali ke main hall untuk acara penutupan. Waktu kita Jumat, kita perlu sholat Jumat, jadi ada waktu sekitar 15-20 menit lagi. Mana teksnya ini? Ladies and gentlemen, may I kindly request all participants and presenters to make their way back to the main hall of Graha Cakrawala Universitas Negeri Malang, as we will now begin the closing and awarding ceremony of the best presenters of the 4th ICMIA 2026. Please kindly take your seat. We will begin shortly. Bapak, Ibu, dan teman-teman semua dimohon untuk segera menempati posisi di Aula Utama Graha Cakrawala Universitas Negeri Malang untuk kita bersama-sama mengikuti acara penutupan dan pemberian penghargaan kepada presenter terbaik untuk kegiatan kita ICMIA 2026. Nanti itu saya umumkan di belakang, Pak, setelah closing ceremony, Pak. Oke, insya Allah betul. Oke, gini. Nanti next-nya di Bandung ya, Pak ya? Okay, distinguished delegates, ladies and gentlemen, and now this is one of the most anticipated moments of the 4th ICMIA 2026. The scientific committee has carefully evaluated all presentations over the past 2 days, yesterday and today's presentation, and we are now proudly would like to announce the recipients of the best presenters for the ICMIA 2026. Ladies and gentlemen, please join me in congratulating our winners, and we would like to invite all the names I will be mentioning after this to the podium to receive the certificate of the best presenters from the chairman of ICMIA and also the president of IMS. The best presenter goes to Hanif Yoma from University Gajah Mada. Please come forward. The second best presenter, we would like to invite to the podium Dia Rizky Arum Wulandari from Universitas Negeri Malang. Please come to the podium. Dia Rizky Arum Wulandari. Where is she? Alright, next one. The best presenter also goes to Abdullah Faizal from Brawijaya University. Please come to the podium. Abdullah Faizal from Universitas Brawijaya. Alright, the next, we would like to invite to the podium for the next best presenter, Sofia Dewi Nur Anissa from Universitas 11 Maret. Sofia Dewi Nur Anissa. Please give a round of applause to Sofia Dewi Nur Anissa. Next, we would like to invite also Melania Tambunan from Sriwijaya University. Melania Tambunan from Sriwijaya University, please come to the podium. Next, the best presenter goes to Maya Aisyah Maharani from Gajah Mada University. Please come to the podium. The next best presenter goes to Fadila Putri Kinasi from Universitas Negeri Malang. Fadila Putri Kinasi, you are kindly invited to come to the podium, please. Okay. The next, Rifki Al-Babila from Universitas Islam Negeri Sunan Gunung Jati. Please kindly come to the podium. The next best presenter goes to Laili Fitri from Institut Teknologi 10 November. Alright. And last but not least, please come to the podium, our best presenter for today's conference, namely Gwen Sivalin from Bandung Institute of Technology. Round of applause. We would like to invite our chairman, Professor Dr. Ahmad Taufik, and also the president of Indonesian Magnetic Society to come to the podium to deliver the certificates or appreciation to our best presenters. And take photo together. Okay, once again, the scientific committee also would like to invite Winda from Universitas 11 Maret to also come to the podium. From Universitas Indonesia, I'm sorry, Winda. Camera ready, please. Winda from Universitas Indonesia, please come to the podium. Okay. Congratulations on your excellent achievements once again, and to the best presenters and all participants and all presenters would like to say thank you for your remarkable contributions to this conference. Once again, ladies and gentlemen, please give our round of applause to our best presenters. Okay, let's now take this moment for memorable by taking photo together. Okay, I will count 1, 2, 3, cheers. Maybe we will have some photos of IMS pose, like Laurentian's course. 1, 2, and 3. Okay, now Chakrawala pose. Last one. Okay. All right, thank you very much. Let's give a round of applause again, ladies and gentlemen. You may come back to your seats. And to close this agenda, we would like to invite Prof. Taufik to stay at the podium. We would like to give the time for the chairman of ICMIA 2026, Professor Dr. Ahmad Taufik, to deliver the closing remarks on behalf of the organizing committee. Ladies and gentlemen, please welcome our chairman, Professor Dr. Ahmad Taufik.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen, distinguished keynote speakers, respected invited speakers, honorable presenters, esteemed participants, and ladies and gentlemen. As we arrive at the closing of the International Conference of Magnetism and its application 2026, please allow me, on behalf of the organizing committee, to express our deepest gratitude to all who have contributed to the success of our conference. Over the course of this event, we have witnessed insightful discussion, inspiring presentation, and meaningful exchange of ideas that reflect the spirit of scientific collaboration and academic excellence. The enthusiasm and active participation shown by researchers, academic, professional, and also students from various institutions and countries have truly enriched this conference. We extend our highest appreciation to our distinguished keynote speaker, invited speaker, session chairs, presenter, and also equity program from LPDP, Indonesian Magnetic Society, Universitas Negeri Malang, Institut Teknologi Bandung, Universitas Pajajaran, Universitas Indonesia, Universitas Gajah Mada, Universitas 11 Maret, Institut Teknologi 10 November, and other institutions from Indonesia, also from names from Japan, from Taiwan, from Thailand, from South Korea, and from other countries. Please know that your presence here and your support are simply appreciated and highly valued. We also express our heartfelt thanks to entire organizing committee and volunteer for your dedication, your hard work, and commitment throughout the preparation and execution of this conference. We sincerely hope that our knowledge that we share, our collaboration, initiation, and the friendship established during ICMIA 2026 will continue this conference and contribute positively to the advancements of science, technology, and also humanity. Finally, we apologize for any shortcoming during this conference and thank you for your understanding and support. Thank you again for being part of this conference. We wish you safe travel, continued success, and we look forward to welcome you again at the future ICMIA event. We will meet again. See you in the next ICMIA 2028 in Bandung. Once again, thank you very much and congratulations for all participants, and see you again. Goodbye. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Prof. Taufik, for the closing remarks. Now, ladies and gentlemen, this agenda will not be possible to happen if there were not Indonesian Magnetic Society. And therefore, as the final closing remark, we would like to kindly invite the President of Indonesian Magnetic Society, Professor Agustinus Agung Nugroho, to come to the podium. Ladies and gentlemen, please give your round of applause to Prof. Agung.
Okay, ladies and gentlemen, as we come to the end of this conference, I would like to take a moment to reflect the incredible journey we have yesterday and today. And I think the conference lift up the topics of energies. So I think for researcher in Indonesia, energy is still a hot topic, and I think this is also opportunity for us to bind, and maybe we can collaborate to get a support from the government, and especially the one which is already applied to some technology. I think the fundamental until the industrial application, the IMS are very eager to support the collaboration so that we can continuously support also our activities. And at the end, as already mentioned, we welcome you to next ICMIA 2028 in Bandung. So at the end, I also would like to say goodbye to all of you, and we hope that we can meet again and strengthen our collaborations. So welcome to ICMIA 2028 in Bandung. So additionally, Bandung is not only just buildings, but we have also some interesting touristic site, including a volcano. So we'll bring also you to volcano, not just seeing these buildings. So hopefully you can come again and join ICMIA in 2028. Thank you.
Thank you very much, Prof. Agung, for your visionary closing remarks. And you can see that Indonesian Magnetic Society has committed to advancing the science and magnetism in Indonesia and also all across the world. Sekedar pengumuman Bapak Ibu, ada tas hilang tadi ditemukan, yang merasa kehilangan tas bisa menghubungi meja registrasi di depan. So attention to all participants and guests. A lost bag has been found, and if you believe it belongs to you, please collect it in the registration desk. And ladies and gentlemen, esteemed colleagues and friends, on behalf of the organizing committee of the 4th ICMIA 2026, also the Indonesian Magnetic Society and Universitas Negeri Malang, we would like to extend our deepest gratitude to each and every one of you. Please do enjoy the rest of your time in Malang and also Bromo tomorrow, and enjoy our beautiful city of education and culture. This concludes the 4th International Conference on Magnetism and its application, the 4th ICMIA 2026. Again, we look forward to welcome you in the 5th ICMIA in Bandung in 2028. Wassalamualaikum warahmatullahi wabarakatuh. Thank you very much. Ini info penting, makan sudah tersedia di sebelah kanan atau di arah selatan main hall Geraha Cakrawala, dan sholat Jumat untuk Bapak Ibu dan teman-teman yang beragama Islam bisa dilaksanakan di Masjid Al-Hikmah sekitar 100 sampai 150 meter dari sini ke arah selatan. Terima kasih.
The Indonesian Magnetic Society, or IMS, is a professional organization dedicated to advancing magnetism and magnetic materials in Indonesia. Rooted in the historic Magnetic Club conferences from 1999 to 2015, IMS was officially established in 2018 to continue and expand this legacy. Today, IMS serves as a growing hub connecting researchers, engineers, industry professionals,